Curvilinear motion. We're going to use normal and tangential components now for motion of a particle along a curved path. And sometimes these coordinates are called path coordinates. And they're different from the polar coordinates in that we're not going to start by differentiating a position vector to get velocity and acceleration. We sort of start right in at velocity. And the way a good explanation is if you were driving around a racetrack and someone asked you to describe your motion, you'd point out the window and you'd say, I'm going that way. Okay, you'd be conscious of your velocity, and that's always instantaneously tangential to your path. If you're driving around a racetrack, you may not be conscious of how far you are from your house and what angle is the position vector from your house to your car. That r and theta with respect to your house is probably not going to be very interesting as you're driving around a racetrack. So let's think about path coordinates, and we'll worry about a tangential unit vector. And since we always want to have two perpendicular unit vectors, we'll define a normal unit vector, but it'll always be toward the center of curvature. So we're going to begin by considering the velocity vector, which is going to be in the tangential direction. Okay, so here on the bottom, this figure shows velocity vector that's tangent to the path. And one thing you'll notice about this path is for a given path, the radius of curvature is always going to change, possibly. So right here I'm drawing an r vector, and for a split second we can think of our motion on the path as being around a circle with radius rho. And then a little bit later we have a new center of curvature, O prime, and now our position vector r is with respect to that new O prime, and we have a new radius of curvature rho. And at this second instant in time, we're imagining ourselves going around a circle with a new radius rho. So there's a theorem that says that for any curved path, you can treat your motion at an instant as being as if it was circular, just for that split second. Okay, so now we're concerned with we're going that way direction, and we're concerned with there's the center of curvature direction. Okay, so moving on to page 19, if we contrast this with polar coordinates, in polar coordinates the UR and U theta directions are not tangent to and normal to the path, as I've said in lecture, but the velocity vector will be. So you've got one velocity vector as you're driving in your car, and we can express it as being tangent to the path. So here's velocity v, which is your magnitude times your tangential unit vector, and then your normal unit vector is going to be perpendicular to that, but in towards the center of curvature. So you can see the difference between the UR and U theta directions and the UT and UN directions. So the velocity vector that's VUT, that's the same vector that's equal to r dot UR plus r theta dot U theta in polar coordinates. Okay, so we're starting with velocity and imagining ourselves always going around in a circle, but the center of curvature and the radius of that circle change from moment to moment. Okay, so the velocity vector is fairly straightforward. Now if we want to differentiate that to get acceleration, well, acceleration should still be the derivative of velocity vector with respect to time, and that's going to be d by dt of s dot ut. The magnitude could change, so we're going to get a tangential acceleration, s double dot ut, and the path direction's changing, so the tangential unit vector is changing direction, so there's going to be a du dot dt. And by now, hopefully, deriving that should be fairly straightforward. So here in figure D, we have a velocity vector, v, and S dot is the magnitude of V. And if we have a center of curvature that's instantaneously rho, and if we sweep out a small angle d theta, then S dot is velocity, which is rho theta dot. Okay, so how does the tangential velocity, how does the tangential unit vector change as we sweep through this angle d theta? Well, here's our initial tangential vector. Here's our final one. These are unit vectors of length 1 that are sweeping through an angle d theta. So here's delta ut, the change in the tangential unit vector. So in the spirit of previous discussions, dut by dt, the arc length of that dut is going to be 1 d theta. So this differentiated vector magnitude is going to be d theta dt. Actually, let me just take a step back here. du tangential, magnitude is going to be 1 d theta. And look at the direction. This vector changes in the normal direction. So dut is d theta un, du theta dt is going to be d theta dt un, or theta dot in the normal direction. So now if we substitute that into our emerging acceleration equation, we'll get acceleration is s double dot ut plus s dot, instead of dut dt, we'll have theta dot un. We can write that as s double dot ut plus, well, s dot we said up here was rho theta dot, so we can have a rho theta dot squared un, and that magnitude is going to look a lot like the r theta dot squared we saw from the polar coordinate days. And we can also express this normal acceleration as v squared over rho, because v is rho theta dot. Okay, so I'll put that in a box, and in the text, that's equations 1218, 1219, and 1220, where they identify this s double dot as tangential, and they identify the v squared over rho as normal. So there's normal and tangential acceleration in normal tangential components. Now every now and then we have a third dimension involved, as we did for cylindrical coordinates when we did polar. If you have a third dimension, sometimes you want to define that third unit vector. And the way the Hibbler text sets it up is it defines a UB vector, which it calls the binormal vector. And the direction of that is such that the cross product UB cross UT should give you UN. Okay? So you don't see that very often, but if you want that third dimension, a good consistent way of setting up the right-handed coordinate set is to have binormal crossed with tangential equals normal. All right, at this stage we are ready to begin some problems involving normal tangential components, and following that we'll have a discussion of what kinds of problems lend themselves to polar coordinates, what kind lend themselves to rectangular, and when should you use normal tangential, because there's going to be a bit of an art to selecting your coordinate system, especially when you get into an exam situation where the problem is not going to be from the polar section of the book and so on. Okay, thank you, good night.